Today we are going to be talking about Lewis dot structures. But before we start drawing, there's a rule that we have to keep in mind, the octet rule. The octet rule states that atoms gain, lose, or share electrons to achieve a full outer shell with 8 valence electrons. This is to achieve the configuration of a noble gas. This rule applies when making Lewis dot structures unless the atom is an exception. Some exceptions to the octet rule include hydrogen, which has 1 bond, beryllium, which has 2 bonds, boron, which has 3 bonds. These exceptions may have less than 8 valence electrons to complete the outer shell, but exceptions that may have more than 8 valence electrons to complete the outer shell include phosphorus, which has 5 bonds, sulfur, which has 6 bonds, and chlorine, which has 7 bonds, and then everything beneath those elements on the periodic table. So now that we have the octet rule and its exceptions, we can start learning how to draw Lewis dot structures. Step 1. Figure out how many valence electrons the molecule contains by looking at the group numbers in the periodic table and the molecule's charge. You will have to add the number of valence electrons of each atom to get the total amount of valence electrons in the molecule. If the charge of the molecule is negative, then you will add the number of the charge to the total valence electrons, and if the charge is positive, then you will subtract. Okay, so we are going to find the Lewis dot structure of CO2. So the first step is to figure out how many valence electrons the molecule contains, like the total number of valence electrons. So what we're going to have to do is we're going to have to look at the periodic table at the group numbers to find out how many valence electrons are in each atom, and then we will add those together to see what the total amount of valence electrons are. So we know that carbon has 4 valence electrons because that's the group number, and that oxygen has 6 valence electrons. And since it's O2, we're going to have to multiply 6 times 2. So we have carbon, which is 4, plus oxygen, which there are 2 of them, and then we have to multiply that by 6. So 4 plus 12 is obviously 16. So that is the total number of valence electrons in this molecule. Step 2. Draw bonds connecting the center atom, the most electronegative atom, to the outer atoms, which are less electronegative. So now that we know that, we can go on to the second step. So what we're going to do first is we're going to draw the bonds connecting the center atom, which is the most electronegative atom, to the outer atoms. So since there's only one C, it's also the most electronegative. That will go in the middle. So we have C, O, and O. And we're going to bond those together. Step 3. Subtract the number of bonding electrons, the number of bonds times 2, from the total valence electrons of the molecule. So we have 2 different bonds, and there are 2 valence electrons in each bond. So what we're going to do is subtract 4 from the total amount of valence electrons because we have 4 valence electrons that we've used already. So minus 4. Now we have 12 valence electrons that we can use up. Step 4. Distribute the valence electrons evenly among the outer atoms to achieve octets if possible. Okay, so now we're going to distribute the valence electrons evenly among the outer atoms to achieve octets if possible. So what we're going to do is try to achieve octets. So we have 12, which means you can put 6 on each O. Okay, so we have octets on the O here because there's 8 valence electrons on each one, but C is not an exception, and it only has 4 valence electrons on it right now, so we're going to have to make a change. If there are any excess electrons, put lone pairs on the center atom. A lone pair is a pair of 2 valence electrons that remain on one atom and are not shared. And this definition is from the AP Chem textbook. Step 5 does not correlate to this molecule, so we already did step 6, is check for octets, which there is not an octet on C. Step 6. Check for octets on each atom that require one. So basically the atoms without exceptions. So we're going to have to do something else. Step 7. If octets are still not achieved, you may need to double or triple bond atoms. Step 7 says that if octets are still not achieved, you may need to double or triple bond atoms. So I think that's something we should try. So if we write this out again, we're going to have C, O, and O. So if we try double bonding the O's to the C, so let's say we have 16 valence electrons, so we have 4 bonds, so we're going to do 4 times 2, which is 8. So we're going to subtract 8 from the valence electrons, which is 8 again. And now if we distribute evenly among the outer atoms, we're going to put 4 on each atom. And now we have octets for each of the atoms, because we have 2, 4, 6, 8 for the oxygen, and then 2, 4, 6, 8 for the carbon, and then the same for this one. So this is our Lewis dot structure for CO2. Okay, so now that we've found the Lewis dot structure of CO2, let's try another example. The next molecule we're going to find the Lewis dot structure for is NH3. So we remember that the first step is to find the total number of valence electrons in this molecule. So nitrogen has 5 valence electrons because it's 5A. And then hydrogen has 1 valence electron, but we're going to multiply that by 3 since there are 3 of them. So we have 5 plus 1 times 3, which is 8. So NH3 has 8 valence electrons total. So now we know that next we have to connect the center atom with the outer atom with bonds. So we have H, H, and H. And then we have 3 bonds right here. So we already know that we can subtract 6 from the total amount because there's 2 valence electrons in each one. So now we only have 2 left over. And since hydrogen is an exception, it can have 2 valence electrons to complete its outer shell. So technically, all these hydrogens have completed octets, or well, not octets, but they have completed shells. So nitrogen is not an exception though. So we have 6 valence electrons on nitrogen right now, and we have 2 left over. So we can go to step number. We can go to step number 5 now. Step number 5 applies to this one because we're going to end up putting a lone pair on one of the atoms. So since N is the center atom, we can put 2 on here because that's a pair, and then 2 valence electrons will complete the octet for nitrogen because there's 2, 4, 6, 8. So that is our Lewis dot structure for NH3. Okay, so we're going to try one more example just so we get the concept down. The last molecule we're going to find the Lewis dot structure for is going to be CH4. Okay, so again, we have to find the total amount of valence electrons in this molecule. So we know that C has 4 valence electrons, and H also has 1. So we're going to have to do 4 plus 4 times 1, which is 8. So we know that CH4 has 8 valence electrons total. So C is going to be our center atom in this case, and we're going to put 4 H's around the C. Then we're going to bond the H's to the C. And this molecule actually ended up being very easy because we have 2, 4, 6, 8. And hydrogen is an exception, and it can have 2 electrons to complete its outer shell. And C ends up having an octet right here because we have 2, 4, 6, 8. So this is our Lewis dot structure for CH4. Okay, so now that we've covered how to draw Lewis dot structures, I would like to explain the geometry of the molecules. There are multiple different kinds of molecular geometry structures, including linear, trigonal planar, bent, trigonal pyramidal, trigonal bipyramidal, tetrahedral, and octahedral. Those are some of the main ones. Some of the other ones are a little trickier, but we're not going to go into those ones right now. But a linear molecule is going to look something like this. I'm just going to use A and B as an example for the atoms. So A is going to end up being the center atom for these examples, and B is going to be the outer atoms. So we have, for a linear molecule, we're going to have 3 atoms, so 1 center atom and then 2 outer atoms. And this molecule is going to have 2 bonding pairs. So this is what a linear molecule looks like. And since it's linear, it's going to be 180 degrees, like the angles of the bonds between the molecules. So that's our linear molecule. The next one we're going to look at is a trigonal planar molecule. So trigonal planar. This molecule is going to have 4 atoms. It's going to have A as the center atom, and it's going to have 3 other outer atoms. So those are going to be B. And then it's going to have 3 different bonding pairs going to each of those outer atoms. So this is what a trigonal planar atom looks like. Here's more of a 3D version of it right here, if you want to see what that looks like. And the degree of the angle between these atoms and the center one is going to be 120 degrees. So that's what it is for a trigonal planar atom. Here, wait, I'm going to write the number of bonding pairs of electrons for each structure. So this one has 2, this one has 3. So bonding pairs. Okay, the next structure we're going to look at is a bent molecule. So for bent molecules, there can be 2 different kinds of structures. One is going to be more of a trigonal planar looking type structure, and one's going to be more of a tetrahedral, which I will cover later. So bent molecules are going to have lone pairs on them. So we're going to have the center molecule, A. This is the more of the trigonal planar version of it, where it only has 2 outer electrons, or 2 outer atoms, I should say. It's going to have 2 bonding pairs, but then it's also going to have 1 lone pair. So that's what a bent molecule looks like. This is, I don't have a 3D picture of it exactly, but this is what it's going to look like. And then the angle degree is going to be less than 120 degrees because the lone pair is going to push these down a little farther. So this is going to be, let's see, less than 120 degrees. And it has 2 bonding pairs, but then it's going to have 1 lone pair. So these ones don't have any lone pairs. The other kind of bent molecule we're going to look at has 2 lone pairs and 2 bonding pairs. So this one is going to look like this. A, B, B. Then we're going to have 2 lone pairs. It's going to look more like that. So the bond angle for this, so the bond angle for tetrahedrals is 109.5. So the bond angle is going to be less than 109.5 for this. So this one has 2 bonding pairs and 2 lone pairs because we have 1, 2, and then 1, 2. So this is the molecular geometry for bent molecules. Next one we're going to look at is a trigonal pyramidal molecule. This molecule is going to have 3 bonding pairs and 1 lone pair. So bonding and lone. 3 and 1. So it's going to have the center atom, and then it's going to have 3 outer atoms, 3 bonds. Then it's going to have a lone pair right here. So this is what a trigonal pyramidal molecule looks like. And then the degrees is also going to be less than 109.5 degrees as well. The next one we're going to look at is trigonal bipyramidal. Which is slightly different than trigonal pyramidal. So this molecule is going to have 5 bonding pairs and 0 lone pairs. So we're going to have an A, then it's just going to be 1, 2, 3, 4, 5. And when you look at the actual molecules, you'll end up changing the atom to whatever the molecule is. So this is what a trigonal bipyramidal looks like. And then I have a 3D example for this one because some of the angles are different. We have a 90-degree angle right here between these two, but then like when you get to a different part of the molecule, it's 120 degrees. And then if you were to look between like these two, it would be more like 180 degrees if it's a straight line. So this is what a trigonal bipyramidal molecule looks like in like 3D. So we have 120 degrees, 90 degrees, and then that's basically it for trigonal bipyramidal. So we have 2 more left. We're going to have a tetrahedral. And this one makes sense because tetra is like kind of like another word for 4, and then we have 4 bonding pairs for this one and 0 lone pairs. So this one's pretty simple. You just have A, 1, 2, 3, 4. And then we're going to connect these. That's your tetrahedral, and the degrees between these is going to be 109.5. So this is what a tetrahedral looks like. So the last one we have here, I'm just going to write it over here so I have more room, is an octahedral. This is going to have 6 bonding pairs and 0 lone pairs. So it's going to look like this. 1, 2, 3, 4, 5, 6. And then we have 6 bonds. And that is your octahedral. And these will have 90 degrees in between each of them. And then this is what a 3D version of an octahedral looks like. So, yep. This is the main part of our molecular geometry. So I wanted to go back to the examples we had with the Lewis dot structures and look at what their molecular geometry would be. So CO2 would end up being a linear molecule because it has 2 bonding pairs right here and right here. and then it would end up being 180 degrees angles. So that is our molecular geometry. Our molecular geometry for CO2. Okay, so since NH3 has 3 bonding pairs and 1 lone pair, it is going to be a bent molecule. And the degrees between the atoms is going to be less than 109.5 degrees. So that's our molecular geometry for NH3, because since there's 3 bonding and 1 lone pair. For CH4, we're going to have a tetrahedral. And this is because we have 4 bonding pairs. And we don't have any lone pairs here. And we know that the degrees for tetrahedrals is 109.5 degrees. So this is our molecular geometry for CH4. And that is all I have for loose dot structures, so I hope you learned something, and thank you for watching.